Hello, welcome to the presentation of my algorithms course, homework 5. In this homework, I will solve problems related to radix sort algorithm. So now let's start with a basic practice question on radix sort with base R without even whole solution. Okay, so give me a question. It asks me to implement the radix sort algorithm with a given base of R for a list of positive integers. It asks me to provide a step-by-step explanation and demonstrate its application on the following lists. So we have an array of integers, as you can see, and we are going to use base R equals 10 for this example. So let me stop the video here. I will solve the question and I will come back with the answer. Okay, now so I finished my solution. As you can see, I wrote the whole process of applying radix sort algorithm on this array, and let's see if it is correct or not. Okay, so it says great job, and my step-by-step explanation of radix sort algorithm for the given example is clear and accurate. So now let's see my solution. So the radix sort algorithm is actually done by checking the digits of the numbers in an array rather than comparing the numbers. So it makes it easier to implement, and it has a better time complexity than comparison-based algorithms such as like merge sort, quick sort, and insertion sort. These are comparison-based, and this is a better approach to sorting an array. So now let's see how we've done this. So it gives us an array here, as you can see, 170, 45, 75, 90, 802, 24, 2, and 66, and in base R equals 10 as given in the question here. Okay, so since our base is 10, what does this mean? This means that we have 10 buckets. Imagine 10 buckets. And these are indexed from 0 to 9, just like arrays. Okay, so it indexed from 0 to 9. In the bucket, which is the first bucket actually, with index number 0, we are putting elements with corresponding digit number equals to 0. So we are looking for we are starting by the least significant digit, which is LSD in abbreviation, which is the rightmost digit in an integer. This is the least significant digit in a number. So in first iteration, we are checking elements, the least significant digits, which is the rightmost digit. So in bucket 1, we are putting elements with least significant digit equals 0. In this case, we have 170 and 90. In bucket 2, we are looking for elements with LSD equals 1, which is an empty bucket because we don't have anything that corresponds to this situation. So in bucket 3, we are putting elements with LSD equals 2, which is 802 and 2. In bucket 4, we are putting elements with LSD equals 3. It's again empty because there is no such an element. In bucket 6, we are putting elements with least significant digit equals 5, which is 45 and 75. In bucket 7, we are putting elements with least significant digit equals 6, which is 66. And the bucket 8, 9, and 10 buckets are also empty because we don't have such numbers to put here. So we're done with our first iteration. We checked all numbers least significant digits. Now in the second iteration, we are moving on the second digit of a number. So in bucket 1, we are putting elements with a second digit equals 0. We put 802 and 2 here. 2 has a single digit, and we can count its second digit as 0. Because there is no number here, it only has one digit. And bucket 2, we are putting elements with second digit equals 1. We put nothing here because there is no such element, as you can see. In bucket 3, we are putting elements with second digit equals to 2, which we have 24 to put here. And bucket 4, we are putting elements with second digit equals to 3, which is again empty because we don't have such element. In bucket 5, we are putting elements with second digit equals 4, which is 45. In bucket 6, we are putting elements with second digit equals 5, which is again empty. In bucket 7, elements with second digit with 6, which is 66. In bucket 8, elements with second digit equals 7, which is 170 and 75. In bucket 9, we are putting elements with second digit equals 8, which is again an empty bucket. In bucket 9, we are putting elements with second digit equals 9, which is 90 only. And we're done with our second iteration too, and we move on to the third iteration. In third iteration, we are checking for the third digits of the integers in the array. So in this case, we have lots of numbers with third digit equals 0, because most of the numbers written here are actually have only two digits. So 2, 24, 45, 66, 75, and 90 have 0 in their third digit. And in the bucket 2, we are looking for elements with third digits equals 1. We only have 170 here. And bucket 3, bucket 4, bucket 5, bucket 6, bucket 7, bucket 8 are all empty because we don't have such numbers. In bucket 9, we have elements with a third digit equals 8, which is we only have 802 here. In bucket 10, we have elements with third digit equals 9, which is again empty because we don't have such elements. So we completed our iterations. We checked every digit of the numbers and compared them and put them in correct bucket. And here we have a sorted array here, as you can see, and our array sorted here 2, 24, 45, 66, 75, 90, 170, and 802. So this is basically how we apply radix sort algorithm on our given array. Okay, so our first question has ended. Now let's move on to our second question. Okay, so it gives me a question. In question, it asks me to consider a radix sort algorithm applied to sort n integers in the range of 1 to n squared. And it asks me to discuss the time complexity of each iteration and the overall time complexity of the algorithm. So I'm going to stop the video here. I will solve the question and I will come back with the answer. Okay, so I found the solution for this problem as O(n plus r) times log n squared in the base of r. Let's see if it is correct. Okay, so our answer is correct. Now let's examine how I solve this problem. Okay, let's start by our question, what it asks us. So in our question, consider the radix sort algorithm applied to sort n integers in a range from 1 to n squared. The integers are represented in base of r, and it asks us to analyze the running time of the radix sort algorithm in terms of n and r. So let's move on to my solution. So in an array of size with n and base of r, what we do, we are actually in the base of in the radix sort, we are actually putting the digits of each number in the correct bucket. We have buckets. If our bases are, let's say our r is 10, we have 10 buckets, and these buckets are goes from 0 to r minus 1, and we are putting the digits what corresponds to which bucket it corresponds to. We are putting the digits in the corresponding bucket. So in order to do that, firstly we have to iterate through the array, and we have multiple iterations most of the time. In order to find the total time complexity, we have to calculate the complexity of each iteration. So we need to distribute the n numbers to the r buckets. each element takes O1 time to put it into correct place in buckets. So why it is O1? Because you can think the buckets as an arrays, and let's say in a bucket, the first index of bucket, and we are assigning a number from our array, a digit from our number. So this only an assignment operation, so it takes O1 time complexity. But we have n elements. Since we have n numbers, n numbers, this time complexity goes to n times 1, which is On. This is putting the elements in the correct bucket phase. But in order to put the elements in the correct bucket phase, we have to iterate through each bucket to find the corresponding bucket. For example, let's say our number is 89, and we are looking for the least significant digits. What is the least significant digit is in 89? It is 9, which is the rightmost digit in the number. So we are putting the 9 in the correct bucket, but we have buckets. Let's say our radix sort works on the base r equals 10. We have 10 buckets, and we are iterating through the buckets with the size of 0 to 9. And we have to check every bucket till we get to 9, and we will put it into place. So since we are checking each bucket, this operation takes OR time complexity. In order to find the correct time complexity of a single iteration, we have to combine these two time complexities, which is OR, which is finding the correct bucket, and ON, which is putting the elements in the correct bucket. So the time complexity of a single iteration is n plus r. So we don't have a single iteration most of the time. We are mostly working with multiple iterations, as I said. The iteration count depends on the maximum digit number an integer have in an array, because we have to iterate through each digit. For example, let's look at our previous example, as you can see here. So here we made 3 iterations here. Why? Because the maximum digit number is 3, as you can see from here. It is 3, so we made 3 iterations. And what does this mean? In third iterations, we are checking the third digit, but most of the numbers doesn't have the third digit, so that's why we put them in third digit equals to 0. So we can, because we can show this 2 as 002, or this 24 as 024. There's no difference between 24 and 024, and so that's why we have to consider the maximum digit number an integer have in an array. So we can calculate the total running time by multiplying the iteration running time, which we found as On plus r, which is the single iteration complexity. We can calculate the total running time by multiplying iteration running time and iteration count. We can show this equation as T of n equals to On times d. So n in this case actually n plus r, where d is the iteration count. So we have to find our iteration count. We already said that the iteration count depends on the biggest number, because biggest number mostly has the biggest digit numbers. Let's say, I forgot to write say here. Let's say the biggest integer in our array is x. In worst case, x will be equal to n squared in our problem, because as you can see, it is given here n integers in the range from 1 to n squared. So n squared is the biggest number, and in the worst case we have to work with the biggest number, because biggest number gives us the worst case time complexity, because it makes the time complexity bigger. So x will be equal to n squared because the numbers are in the range from 1 to n squared. So d can be calculated as log x in the base of r. Why? In order to understand this, let's assume that r is 10, which is a general case because most of the problems has a base of 10. But it can be 20 or 5 or other numbers, but most of the time the r equals to 10. In this case, we have to divide the number by 10 each time to find the last digit. For example, let's say, I wrote m here, but it is actually the biggest number. It represents the biggest number, but it should be x. So this is x actually. X is 789. In order to find the least significant digit, which is the digit at the rightmost, we have to divide it by 10. When we divide it by 10, we found the last digit. So when we divide it by 10, we get 9. So this is the first iteration. Then we put the 9 in the correct bucket. This is the first iteration. And then we are dividing the rest, which is 78. Because we are working with the third digit, we have to look the other two digits, which is 78. And when we divide it by 10, we get 8, which is the second iteration. Then we put the 8 in the correct place, which is the bucket with the index number 8. And 7, which is the third iteration, which is the only number left. So we can see that it depends on the digit number of x. That's why the d is log x in the base of r. Why it is logarithm? Because we are dividing by 10 each time. That's why the logarithm in this particular example, it is actually log x in the base of 10. So we said that our biggest number is n squared in our case. When we put these in the correct place, we get O n plus r times log n squared in the base of r. So in here we found the d, which is the iteration count, and we found O n plus r, which is the time complexity of a single iteration. So the total time complexity goes like this, and as you can see, it is a correct solution. So this is all about my homework.